So if you are listening to this, you have likely spent, countless hours tuning recurrent neural networks or like optimizing transformers or wrestling with state space models.
Oh, absolutely. The endless hyperparameter tuning.
Right, because you already know the operational reality of dealing with time-ordered data. I mean, whether you are processing high-frequency limit order books or multidimensional electronic health records or just really complex natural language.
Yeah, and the pain points are always exactly the same.
Exactly. You get vanishing gradients over long horizons, or you do that endless trial and error of engineering rolling window features. And let's not even talk about the massive compute budgets required to just force these continuous underlying dynamics into our discrete computational graphs.
Right, because traditionally we just feed our models an array of observations. We treat the data like a rigid flip book, state one, state two, state three.
Yeah.
But the actual physical processes generating that data do not operate as discrete flipbooks. They are continuous fluid trajectories.
And when we force that fundamentally continuous dynamic into a pointwise discrete sequence, we introduce these severe geometric blind spots into the modeling pipeline.
We are quite literally discarding the spaces between the observations. And, those spaces often contain the definitive structural information about how the system is actually evolving.
Yeah, that structural blind spot is exactly what we are dismantling today. So, welcome to the deep dive. Since you already operate at an expert level in machine learning and mathematics, we are bypassing all the basic definitions of sequential modeling today.
Thank goodness for that. We can jump right into the good stuff.
Right. The mission today is to thoroughly unpack this paradigm-shifting theoretical framework detailed in a paper called A Primer on the Signature Method in Machine Learning by Ilya Chevyrev and Andrey Kormilitzin.
It is such a brilliant primer. The core proposition they make here is a radical inversion of the standard ML pipeline.
Yeah, instead of forcing data into discrete sequences, we embed discrete data into continuous multidimensional paths.
Exactly. And from there, we extract this non-parametric mathematical object called the signature of the path.
Okay, let's unpack this because the underlying mathematics draw on K.T. Chen's seminal work on iterated integrals from, the 1950s?
Yeah, the 50s, which was then radically expanded in the 90s by Terry Lyons through rough path theory.
Right. And the authors of this primer have essentially translated all those really deep results from stochastic analysis into a highly scalable, totally deterministic feature extraction pipeline.
It's honestly a mathematically rigorous way to capture both the chronological and geometric properties of any sequence.
So let's just get straight into the formal definition. We have this continuous mapping, let's call it $6, from a time interval to $, into a d-dimensional real space, math B interval.
Right.
If I am trying to build a feature representation of this trajectory, I need to know exactly how the signature is constructed.
So the signature of the path integrals, which we denote as exec from Ilya to Balalar, is an infinite sequence of iterated path integrals. And the construction is recursive and, highly systematic.
Okay, so where do we start? Level 0.
Yeah, by convention, the 0th term of this sequence is just the scalar one. But moving to level 1, we compute the path increments along each of the coordinates. You just integrate the differential dollars from time of right at $1.
Which, just applying the fundamental theorem of calculus, that just yields $6 at minus $6 a dollar.
Right.
It is simply the net displacement along that specific axis.
Exactly. But as you know, single displacements don't capture the internal routing of the path. You take 3 right turns, your net displacement might be 0, but your path was complex.
Right. The increments are totally blind to the journey.
So to capture that routing, you have to move to level 2. Here, you compute all the double iterated integrals. For any pair of coordinates, say EH-LR, you integrate the level 1 increment $, against the differential of coordinate $.
Oh.
And crucially, this integration happens over a 2-dimensional simplex.
Wait, let me stop and visualize that simplex algebraically because the boundaries of integration are where the causality of the system is enforced, right?
Yes, exactly.
So the simplex is this region, let's call it delta 2, where time seller is strictly less than time sellers. We are not just computing the product of 2 independent integrals.
No, not at all. Because cells is less than Taylor, we are accumulating the entire historical displacement of coordinate dollars strictly up to the exact infinitesimal moment that coordinate dollar undergoes its change.
Wow, so it is literally enforcing the arrow of time.
The arrow of time is the foundational property here, and you just repeat this recursively for level 3, integrating over a 3-dimensional simplex, where $2 is less than tori. which is
Sure.
less than $1.
Which yields the triple iterated integrals.
Right. And you literally continue this out to infinity. The result is this infinite sequence of tensors constructed along all possible multi-indexes or words built from an alphabet of your dollar coordinates.
You know, looking at this sequence, a structural analogy comes to mind. In classical calculus, the Taylor series gives us an infinite algebraic sequence of derivatives that perfectly describes a local function around a point.
Yeah, a perfect local approximation.
Right. So is the signature essentially a Taylor expansion, but like operating globally on the entire continuous path rather than locally on a function?
The mathematics support that analogy directly, actually. The signature serves as the natural generalization of polynomials to the space of paths.
Oh, that's fascinating.
And just as Taylor expansions form the basis of function approximation, the signature provides a universal basis for continuous path approximation.
But there's a catch, isn't there?
There's a critical distinction. The algebra of signatures is strictly non-commutative.
Because the order of integration matters. I mean, integrating coordinate 1 prior to coordinate 2 over the simplex yields a fundamentally different physical quantity than integrating 2 prior to 1.
A completely different quantity. The sequence of events alters the final state, which, perfectly mirrors the reality of almost all complex dynamical systems.
Okay, so an infinite sequence of non-commutative iterated integrals is mathematically elegant. Sure. But as someone engineering ML architectures, I really have to push back here.
Go for it.
Why are these specific iterated integrals the uniquely correct features for sequential models? I mean, there are countless ways to extract frequency domain or time domain features. Why rough path theory?
It's a fair question. The justification lies in the theory of controlled differential equations, or CDEs.
Sure.
Let us assume you have a dynamic system driven by your path $6.
Okay.
We can write this formally as y_a_ti equals v_at time, where the is the state of your system, and v_var represents a collection of vector fields defining the system's underlying physics or, mechanics.
Okay, so if I want to solve for the state dollars the end of the time interval, historically, I would reach for Picard-Lindelof iterations.
Exactly. The classical approach.
You take an initial constant guess for the path, integrate that constant through the vector field dollars to get a slightly better approximation, and then recursively feed that new approximation back into the integral.
Right. But watch what happens when you execute those classical Picard iterations. A really profound separation of variables occurs.
How so?
If you write out the first few iterations, you end up substituting the integral equation back into itself. You get terms like the integral of the derivative of dollars multiplied by dollar integrated against vigors and difficals again. Notice what is happening to the driver's vigor.
Oh, I see it. The geometry of the driving path $6 is completely separating from the vector fields.
Yes.
The vector fields just yield these regular derivatives, but the Decker terms stack up into multiple nested integrals. They form the exact simplices we just defined.
Precisely. As you push the Picard iterations to infinity, the solution for the final state $6 is deterministically expressed as an infinite linear combination of the signature of $6.
So the vector fields just provide the constant coefficients.
Exactly. The signature dictates absolutely everything about how the path interacts with any dynamic system it drives.
That is wild. And that mathematically validates figure 5 from the paper, which really highlights a massive vulnerability in standard modeling.
Oh, figure 5 is the perfect illustration of this.
Yeah, suppose you have a path, let's call it 6s, representing a baseline signal. Then you have a second path, 6 which is the exact same signal, but corrupted by a highly oscillatory microscopic perturbation.
Right. In terms of the standard uniform norm, the maximum topological distance between $6 tilde at any time dollars is just epsilon. They are microscopically close.
Right. If we sample them at discrete points, like our traditional flipbook approach, a uniform norm distance metric would classify them as virtually identical.
Totally identical.
But if you take those two paths and use them to drive a nonlinear differential equation, their final states diverge completely. The high-frequency noise accumulates and just derails the entire dynamic system.
Because point-wise sampling fails entirely to capture the dynamic reality of the paths. It cannot see the path length or, the areas being continuously swept out by that high-frequency noise.
But the signature captures that divergence perfectly.
It does. It proves that the uniform norm is an inadequate metric for interacting dynamic systems. The signature, on the other hand, inherently maps the true operational topology.
I mean, I definitely understand the theoretical imperative now, but translating this into an applied ML pipeline presents a massive computational wall.
Oh, for sure. Infinity is hard to compute.
Yeah, I have an infinite sequence of tensors. I can't exactly pass an infinite, highly redundant array into a neural network without my memory exploding. So how do we compress this algebra into a usable feature matrix?
Well, before we compress it, we must leverage a structural property that drastically simplifies the problem, and that is time reparameterization invariance.
Okay, what does that mean in practice?
It means iterated path integrals are invariant under any smooth, monotonic reparameterization of the time variable.
Oh, meaning the signature exclusively encodes the geometric trajectory traversed through the state space, completely ignoring the velocity at which the path was drawn.
Exactly.
So if I speak a sentence slowly versus quickly, or draw a character fast versus slow, the signature tensor remains identical.
Yep. That invariance is highly advantageous for classification tasks. But to address your computational wall regarding infinite redundancy, we have to look at the true algebraic engine of this framework.
Here's where it gets really interesting.
It is the shuffle product.
Let me set up the shuffle product algebraically for the listener. Say I want to multiply two separate elements from the signature together. For example, the integral over a multi-index $8 multiplied by the integral over a multi-index dollars.
Right. So if you multiply those two integrals, the result is mathematically equal to a linear combination of strictly higher order signature terms.
Wait, really, just a linear combination?
Yes. Specifically, you sum over all order-presuming shuffles of the two multi-indexes.
Okay, so if we imagine multi-index $E a red deck of cards and D as a blue deck, we interleave the two decks in every possible combination.
That's a great way to picture it.
The internal chronological order of the red cards remains strict, and the blue cards remain strict, but they weave together. The mathematical consequence here is profound. Multiplying two integrals over their respective simplices naturally equals the sum of integrals over higher dimensional simplices.
And that consequence establishes that the signature elements form a shuffle algebra, meaning any polynomial function of the signature can simply be rewritten as a linear combination of signature elements.
But that also reveals massive feature redundancy, doesn't it?
Massive redundancy. For example, the level 2 symmetric term is mathematically constrained to be exactly half the square of the level 1 increment.
Oh, I see. Which means if I feed the raw signature into a linear classifier, I am carrying around redundant feature dimensions that offer zero new information, just pure computational overhead.
Exactly. So to resolve this, the authors rely on the log signature. We operate in the algebra of formal non-commuting power series and just take the formal logarithm of the signature sequence.
By applying the standard Taylor series expansion for the logarithm.
Exactly.
Sure.
And by doing that, we systematically strip out all of the redundant symmetric information.
So the resulting features compress strictly into the free Lie algebra. Every element of the log signature is constructed entirely from Lie brackets, the commutator of $60 and $6, $6 minus $6, $6.
The log signature is the computationally optimal feature set. It retains the exact same descriptive power as the infinite signature, but uses the absolute minimal possible number of parameters at any truncated depth.
I want to ground these Lie brackets in a physical reality, though. The level 1 signature is just the net displacement vector. What is the physical meaning of the level 2 anti-symmetric Lie bracket?
Oh, it has a beautiful geometric interpretation. It represents the Levy area.
The Levy area.
Yeah. Visualize a path wandering through a two-dimensional plane. Now, draw a straight geometric chord connecting the absolute starting point to the final ending point.
Okay, got it.
The Levy area is the signed area enclosed between the wandering trajectory of the path and that straight chord.
So it measures the deviation from linearity. It quantifies the bulge or the curvature of the trajectory in that 2D projection.
Exactly.
That provides incredible geometric intuition, but now we have to bridge the gap from abstract continuous integrals to the discrete data you and I work with daily. We start with a CSV file, right? An array of observations at times $2, 2 under 1, up to 2 and 1, 1. How do we apply Chen's continuous integration to this discrete data?
Right. The empirical pipeline relies on embedding. We take the discrete points and interpolate between them to synthesize a continuous path.
Makes sense.
Then the signature of that resulting path is computed, truncated at a specified depth, and that log signature tensor becomes your ML feature matrix.
But the choice of interpolation is not trivial, is it? I mean, if I use piecewise linear interpolation, like drawing direct diagonals between points, I get a totally different topology than if I use rectilinear interpolation, where I move purely along the axis like a staircase.
You're entirely correct. The mapping methodology fundamentally defines what information the signature extracts. This is why we use auxiliary transformations. And the most mathematically powerful one is the lid lag transformation.
Okay, let's visualize the lead lag transformation carefully. We take a one-dimensional discrete time series and duplicate it into a two-dimensional space.
Right.
We create a lead path, which jumps forward to the next value, while the lag path stays fixed at the previous value. Then the lag path jumps up to catch the lead. So in our 2D plane, this creates a literal staircase pattern moving diagonally upward.
And the analytical beauty of this mapping lies in its levy area.
Yeah.
If you compute the level 2 antisymmetric signature of that 2D lead lag staircase, it perfectly calculates the quadratic variation of your original one-dimensional discrete sequence.
Wait, let's break down exactly why that works. As the lid path jumps forward and the lag path catches up, each step of the staircase traces out a right-angled triangle relative to the diagonal chord.
Exactly.
So the area of that microscopic step is proportional to the square of the increment, right? The change in 6 squared. Summing those geometric areas across the entire path equals the total variance of the signal.
It's stunning, isn't it?
A pure geometric area calculation naturally extracts the statistical volatility of the underlying time series. That's incredible.
The geometry completely encodes the statistics. Furthermore, you can compose multiple mappings. You might take a sequence, compute its cumulative sum, apply a base point augmentation to anchor it to the origin, and then apply the lead lag transformation.
And the result of that.
The signature of that composite path will capture deep cross-temporal statistical moments that standard rolling window feature engineering completely fails to see.
But practically speaking, we are not writing nested numerical integration loops to calculate this in production, are we?
Oh no, definitely not. The paper points to mature tooling, like the eSig package, iSignature, and Signatory.
Okay, good.
Yeah, these libraries provide highly scalable CPU and GPU computations of these tensors. They are fully integrated with PyTorch Autograd for backpropagation.
So the software infrastructure is robust enough to just drop this inside deep learning architectures as a standard pooling or feature extraction layer today.
Yep, it's ready for production.
Which brings us to empirical validation. How do these non-commutative geometric features actually perform compared to standard baseline models?
The authors present a highly intuitive example using the pen-based handwritten digit dataset. Specifically, they focus on classifying the digit over versus the digit 8.
Oh, that is the perfect edge case for sequential models. Because if you track the 6 dollar ordinates of a pen tip drawing a Theodore open and 8 font, in both cases, the pen does a full loop, meaning the starting coordinate and the ending coordinate are virtually identical.
Right, so the net displacement is 0. If you feed this to a model relying solely on level 1 increments, your feature vector is just a sequence of zeros. The model is completely blind.
So how does the signature separate them?
It separates them through that higher order geometric parity we discussed. Think about how you draw an 8.
Yeah.
It crosses over its own path, creating 2 distinct lobes.
Right.
Because those lobes are drawn with opposite rotational orientations, one clockwise, one counterclockwise.
Yeah.
Their signed levy areas essentially cancel each other out.
But a zerom, however, sweeps out a single, large, uniformly oriented convex area.
Exactly. It acts as a geometric parity check. The authors demonstrate that simply plotting the level 2 levy area perfectly clusters the yielders, completely separate from the 8s.
So you don't even need a complex nonlinear model. You can feed that pure geometric feature into a simple linear SVM or like a UMAP-P projection and achieve near-perfect separation.
Yeah, the signature bypasses the noise of pixel densities and sequence lengths, isolating the pure topology of the drawing process. But, the framework scales far beyond simple geometries because of expected signatures.
Right, which bridge these deterministic integrals directly to probability theory. Explain how that bridge is built. If the signature is a deterministic property of a single path, how do we use it to model stochastic processes?
We treat the path itself as a random variable and take the expectation. Just as classical moments like mean, variance, skewness define a standard probability distribution on the real line, the expected signature acts as the exact analog for path-valued random variables.
And the authors invoke the Stone-Weierstrass theorem to prove this, right?
I do, yeah.
I want to clarify how Stone-Weierstrass applies here for everyone. The theorem basically states that if an algebra of continuous functions separates points on a compact space, it can approximate any continuous function on that space.
Exactly.
Because the signature elements form that shuffle algebra we discussed earlier, they perfectly satisfy the theorem.
And the consequence of satisfying that theorem is monumental. Probability measures on compact sets of unparameterized paths are uniquely determined by their expected signatures.
Wow.
If two stochastic processes yield the same expected signature, they are governed by the exact same underlying probability distribution.
That provides a truly rigorous, non-parametric theoretical guarantee. Your feature map is not discarding any statistical resolution.
And that theoretical guarantee is precisely why this framework is currently revolutionizing quantitative finance.
How so?
Well, firms are computing moving window signatures over multidimensional limit order books. The cross terms of the signature inherently capture the correlations between bid-ask spreads and execution volumes across time. It exposes atypical market regimes that standard autoregressive models completely miss.
And we see the exact same power in healthcare telemetry. Researchers are tracking multidimensional clinical vitals in the ICU, computing the signatures, and predicting the onset of sepsis hours before standard threshold alerts trip.
Yes, or utilizing wearable accelerometer data.
Right, mapping the complex 3D trajectory of a patient's gait to classify fall risks in neurological disorders. The signal is entirely embedded in the continuous dynamic evolution of the variables.
The framework just provides a universal mechanism to extract correlations between different variables across different times without requiring the engineer to manually specify those lags.
So to summarize the operational reality here, the signature method provides a mathematically rigorous, dimension-reducing feature map. It translates the chronological order and the topology of complex multidimensional data into a non-commutative algebra of iterated integrals.
Beautifully stated.
It transforms the continuous, often murky dynamics of stochastic time series into a crisp, structural feature tensor, perfectly primed for machine learning algorithms.
If we connect this to the bigger picture, though, the architecture we have discussed today relies entirely on a one-dimensional time parameter defining the sequential path. But the authors leave us with a frontier problem at the end of the primer.
Okay, what's that?
What happens when your underlying data has no canonical sequential order?
Oh, you mean spatial data architectures? Like a 2D medical image, a 3D point cloud, or a graph manifold? I mean, if you try to trace a one-dimensional path through a 3D volume, you inevitably destroy the spatial topology of the data.
Exactly. So to preserve that spatial topology, researchers are currently attempting to generalize the signature method to multidimensional spatial data.
Moving beyond 1D paths.
Yeah, they're employing higher gauge theory and cubical complexes to define expected signatures for surfaces, manifolds, and interacting volumes.
That is the absolute bleeding edge of the field. So I want to challenge you to consider that specific frontier. We began by realizing that treating time series as a discrete flipbook blinds us to the continuous trajectory. But how might you apply generalized spatial signatures to your own multidimensional architectures?
It's a tough question.
It is. How do we map the topology of a three-dimensional tensor into a non-commutative algebra? It forces us to entirely reconceptualize how we extract the geometry of data.